Hi, welcome back to Special Relativity. It's been almost 40 videos and we have talked about how space and time are entangled, how they are plastic and not rigid anymore. We have also seen the deep relation between mass, energy and momentum. We have also talked about how relevant relativity is in particle physics, where we have collisions and transformation of mass into energy and vice versa. We have seen that observing is not the same as seeing, and some deformations take place in the image of the objects we see. But we haven't talked too much about daily real-life application. Probably the most relevant application of relativity, the one that our society uses millions of times every day, is GPS. The Global Position System is a set of satellites that can tell you your position on the surface of the Earth with a resolution of a few meters. Your position has three space coordinates x, y, and z. You need at least 3 satellites to triangulate this. Satellites send an electronic signal, light, to your GPS device, which sends it back. By measuring the time needed by light to go back and forth and knowing the speed of light, they can calculate the distance from the satellite to your device. Because they need 3 coordinates, you need at least 3 of them. There are 24 satellites in orbit around the Earth at an altitude of 20,200 kilometers. But how is it related to relativity? The speeds of our cars are not that high. For just a bit more than 100 kilometers per hour, the time dilation is not relevant at all, isn't it? Well, yes, that's right, but let's calculate the time rate difference between the clocks in the satellites and the clocks on your fast car. Satellites are revolving the Earth in stable orbits. From Newtonian physics, we know that their speed is equal to the square root of Gm over r, where g is Newton's constant, m is the mass of the Earth, and r is the radius of the orbit of the satellite. This is about 4.45 kilometers per second. The speed of a clock at rest in the surface of the Earth is moving at a maximum of 40,000 kilometers in 24 hours. This, of course, depends on the latitude. But for a clock in the equator, this is about 0.47 kilometers per second. Because of the speed difference between the satellite and the clock on the Earth, there is going to be some time dilation given by t equals to t naught over the square root of 1 minus beta squared. Because the speed is very small, beta is way smaller than 1, we can approximate by Taylor expansion and then calculate the difference in time rate between the clock on the satellite and the clock at rest. Let's say at the center of the Earth or at infinity. We can do this also for the clock on the surface of the Earth. Here the radius of the orbit is the radius of the Earth. Now we subtract one minus the other to see the time rate difference between both clocks. If we want to know the time difference per day, we just multiply by how many seconds are in one day. Okay, Before I continue, we need to know something about general relativity. This course is about special relativity, that describes the physics and effects in measures of time and distance due to high speeds. General relativity describes the physics of gravity, of intense gravitational fields. One of the many effects of general relativity is also time dilation created by gravity. Intense gravitational fields pull the passage of time. Gravity dilates time, dilates the
tick-tocks of the clocks,
just as high speeds does. So because our clocks on the Earth experience a higher gravity than the clocks in the satellites, there is going to be an additional time dilation, an additional difference in the time rate between those clocks. And we need to also account for this. The expression from general relativity for this dilation is 1 over the square root of 1 minus 2 gm over r c squared, where r is the distance from the center of the Earth in this case, and m is the mass of the Earth. We should calculate this also and see if it is a relevant effect or not. Because the gravity on the surface of the Earth or in the orbit of the satellite is really small, gm over r is smaller than c squared, we can expand in series of Taylor and substitute for the satellite and for the surface of the Earth. Just as with the special relativistic effect, we subtract one from the other to get the total difference in time rate due to gravity. We multiply by the seconds in one day and get about 45 microseconds. So we have that the clocks in the satellite run slow of about 7 microseconds because of their speed, but they run faster by 45 microseconds because of gravity. So we subtract one from the other and find that per day the difference in time elapsed is of about 38 microseconds. Is that something to worry about? Well, remember that the positions are measured by sending a light signal. The question you want to answer is, how far can light travel in 37 microseconds? Well, the answer is 11 kilometers. After just one day, you would be off by 11 kilometers. GPS would be of no practical use without relativity, both special and general. Think about this every time you use your GPS or you buy something online and UPS or FedEx knocks at your door. May the science be with you.